Okay, so say that again. So we get a common denominator here, but we already have it, so we put that together as one fraction. This, since we're multiplying, we don't need a common denominator, but I like to put the 1 there because it helps me with the canceling. You know, it helps me notice that, well, of course, I can't cancel those, but it gives me a top and a bottom. Okay, now down here, what I need to do is turn this 1 into a cosine over cosine and get a common denominator. So now my bottom then is 1 plus cosine all over cosine. And then what that allows me to do is now flip that up here. Okay, so again, the strategy though is very similar. Write these things in sines and cosines. If you're adding fractions, get them together, because if you can get it together as one fraction, if you can get one fraction on the top, one fraction on the bottom, now here you might say I have two fractions, but they're times, so it's kind of like the same thing. It's kind of like having AB, over C, right? That's fine. I can do some canceling there if I get it looking like that. So now what do I got? Well, sure enough, that can cancel that because what I'm doing is multiplying here. And then this can cancel that. And so now we just have sine plus 1. Okay, which would be, and that's why that one was E. Okay, the key is the common denominator and just kind of keeping track of things. Okay, what else? Anything else on the front? How about the back? The back's getting closer to what we're doing today, where I give you both sides. You got to make it match because you knew it had to be one of these two. Of course, once you start getting the letters at the bottom, you pretty much know what to say. You don't have it back then? Why are you looking at me?
Because you're like, what we're doing on the back today is basically what's on the quiz.
No. No. Not on the quiz. That's where we're going to next. With No.
What are you doing, Chad?
No.
That's what I was thinking.
Yeah, no, after the quiz. After the quiz. Yes.
Number 9.
Number 9. Oh, yeah. Well, it really isn't that bad.
I got close.
Okay.
Close enough.
On this one, I would probably want to make this sine plus 1, sine minus 1, even though I know that could be turned into like a cosine kind of thing. But the reason I do that is, number one, I look over here because, again, when we do these identities, we're going to know what the other side looks like. And I see the bottom being a sine plus 1, sine minus 1 thing. So that is a hint to me that I probably want that to look like that. Okay. Also, I have this sine minus 1, which I could get a common denominator then because it already has a sine minus 1. So all I need is to multiply by a sine plus 1, top and bottom, right? And then I've got a common denominator there. And then this 1 I can just make as a sine plus 1, sine minus 1, and again over sine plus 1, sine minus 1. And now I've got common denominators with everything. Now, remember we talked about how on the top, a lot of times you want to multiply that out, because what we'd like to do as I look at this, I think what I'd like to do on top is combine terms. I'd like to see if some terms can combine. On the bottom, I just want this on all of them. All 3 of them have that on the bottom, right? So the bottom is just going to be sine plus 1, sine minus 1. That's going to be my common denominator, okay? Because I got it here with the 1, I got it here on this one, and I got it on this big one. Okay, so what is this now? What is that top? Let's change color here. So this would be, so I'm going to go ahead and multiply that back through. That'd be sine squared minus 1. This one I'm going to distribute. So that'd be 2 sine squared plus 2 sine. Right? I'm just going to take 2 sine times sine. That's 2 sine squared, 2 sine times 1. And there's plus signs in between all this. And then it's plus all this. So that's a term, that's a term, that's a term, and that's a term. Okay, so let's see what adds together. Here's a sine squared and a 2 sine squared. So that would be a 3 sine squared. Okay, so I use that, I use that. Here's a negative 1 and a plus 1. So those would cancel. Here's a 2 sine and a negative 5 sine. So that'd make a negative 3 sine. Okay, and then I have a plus 2 sine cosine, and I have a minus 2 cosine. Okay. So I think I've accounted, oh wait, yeah, no, I already did that with that. I had that, and then I got that. Okay, I think that's everything. Now, do you see anything on the top there? What do you got? There's 4 terms. Think back to algebra class. Grouping, factor by grouping. Look at these 2. Take out a what? Take out a 3 sine. Look at those 2. Take out a 2 cosine. Okay, so now take out a 3 sine here. You're going to have sine minus 1. That's a good thing. And you got 2 cosine here, and you're going to be left with what? Oh, sine minus 1. That's a really good thing. Okay, so now on top you have 2 things that both have a what? You have 2 things here, this and this, that both have a sine minus 1. So I can take a sine minus 1 out, and I'm left with, if I take sine minus 1 out, I'm left with 3 sine, which of course when I start looking at my answers, I can tell I'm on the right track here. Take out a sine minus 1, I'm left with a 3 sine plus a 2 cosine. Okay, and then my bottom is still sine plus 1, sine minus 1. Cancel, cancel. There it is. Okay, so, okay, but the strategies were very similar to what we've done. It just had a lot of them all the same problem. But noticing what I had on the bottom, so thinking about factoring that, then getting common denominator, and understanding when I get that common denominator, I want to add the tops. That's why you get a common denominator. Well, to add the tops, you need a bunch of terms. So I need to distribute, FOIL this out, distribute. So I had a bunch of terms set there that I can combine. Then once you combine them, see what you can do. The hope usually is when you get common denominators is that when you combine the tops, maybe you can factor and cancel. That's kind of the hope. That's why I usually leave the bottom factored. But the top, you go ahead and multiply out so things combine. And then it turned out it did. We had to do kind of factoring by grouping, which is a little trickier. But there you go. See, as opposed to number 7, and I was helping, we were talking about it this morning, and we even got started. I was looking at their work, and we got started doing cosines over sines, and it was getting real messy. We were thinking about common denominators. This is what I was talking about, how sometimes you just look at one and see it, and sometimes you just don't see it. But what turns out to be the obvious thing on number 7? Pull out not a cotangent, pull out a secant out of the bottom, and you got cotangent plus 5 with a cotangent plus 5 sitting right up there.
Oh my gosh.
Did you not see that?
I spent 10 minutes on this problem.
Yeah, that's okay.
She, well, like, I thought she just, on 7, she just, like, pulled the cotangents, like, factor.
Oh.
I was like, you can't just divide that.
Yeah, oh yeah. Yeah, you can't just cancel like the cotangent.
That's what I thought.
Yeah,
Wait.
yeah. What?
In that case, secant's on the bottom.
Well, right, so you can't stop there. You're right, you can't stop there. So it's 1 over secant, which is cosine. So the right answer is cosine.
Oh yeah, okay.
Yeah.
I got it.
The right answer is cosine. But yeah, you might have done, did you do sines and cosines?
Yeah, it was south. Yeah.
You get the right answer though?
Yeah, I got the right.
Yeah, you can get there, right? I mean, it's just that idea of, yeah. So, it's just that idea of taking the long way, right? You can take the long way sometimes.
The long way, like, it's so hard that I don't want to give up.
Well, it can. Yes, it definitely can. So, you know, like I said, sometimes you see it, sometimes you don't. All right. So let's do this thing real quick here. When you get done, you can keep working on that if you need to. It's not going to take real long, but a few people may take a little longer. If you want to work on a few Excels, I'd like to get started with our identity stuff before lunch, though. So I'll probably stop you on the quiz at some point, but. I mean, no, we can do this real quick.
Don't worry about it.
It's a sign.
was just.
No, it's. Okay, so I mentioned this the other day, and that when we have an equation just means it's something with an equal sign. So you have a left side, you have a right side. Now, we go all the way through algebra, and it's amazing. Even with calculus students, I'll talk to them, and I try to do this in my algebra class. Solving an equation means what? What does that mean? Solving an equation, usually the response is find the answer. Well, okay, but what does that mean? What does it mean to solve an equation? What's it mean to solve x plus 1 equals 3? What's it mean? That's not simplify, no. What does it mean?
Figure out what the equation works.
Figure out what value of x, now you said gets the equation to work. Now what's that mean? What do you mean for the equation to work? Be balanced, or to be true. Okay, equations are true or they are false. It's like a conditional. It's a statement, and it's either true or it's false. We care about when it's true. That's what it means for an equation to work. So solving x plus 1 equals 3 is really saying find all the values of x that will make it balanced, that will make that be a true statement. Well, the only one that works is 2. 2 is the only value of x that makes that be true. All other values of x make this statement be false. Right? So we don't care about those. So when we say solve an equation, that's what we're saying. Find all the values of x that make that equation true. So when we say solve this equation, we're saying find all the values where the sign is 1/2. Well, we know there's how many of those? There's an infinite number of values where sign equals 1/2. We go around the unit circle all day long. Usually when we solve one of these, which we're going to do starting tomorrow and into next week, is we limit ourselves from 0 to 2 pi, right? And so there, if we do that, then it would be pi 6, and it would be 5 pi 6, and we'd have 2 answers, because sine of pi 6 is 1/2, and sine of 5 pi 6 is 1/2. But that's called a conditional equation. It's only true for certain values of x. An identity is an equation that's true all the time, for all values of x. So sine squared equals 1 minus cosine squared. It's not an equation we would solve. It's an equation that is just true. The solution would be all numbers. So that's what we're working with today, identities. Identities are equations that are true all the time. Now what we're going to do is we're going to verify that it's an identity. So this equation equals this equation, or this equals that. We're not saying to solve it. We're saying to verify it. So that's much different, because when we solve an equation, we work across the equal sign. We take away 1 from both sides. Right? Here you might say we do the arc sign of both sides or whatever. When we're verifying an identity, so that's why I put this line down here, and I think it's a good habit for you to get into. I call it a T-chart, and that helps remind me, okay, I'm verifying identity. It's something you have to do in calculus too. It's a verifying that the left side's equal to the right. So we can't cross the equal sign. Okay? We got a left side, we got a right side, and we got to work with the left side, work with the right side. Now, you got a couple of strategies, and we're going to read about them when we come back from lunch. But one of the strategies is work with just the left side and turn it into the right side. Well, that'd be a pretty good one on this one. Okay? So, we use the identities we've been learning, okay, to work with this left side. But it's kind of like the worksheet today where we're trying to match it with some stuff on the other side. The difference is we know exactly what we want to end up with. Okay? So your work is going to be your verify, or your show, or your prove. Well, what's secant squared minus 1? Tangent squared. So a person might start off doing this, right? And then what could we do from there? How about sines and cosines? So we can do sine squared over cosine squared all over, and then secant squared would be 1 over cosine squared. So this seems familiar, stuff we've done. And then what do we do when we get something like that? We flip it. We take the bottom and we flip it. So what do we got? We got cosine squared over 1. So we take that, we flip it up, and what happens? Cancel. We get sine squared theta. What I like to do is draw a little arrow, maybe make a check mark or whatever, and it shows. And we want to literally show that the two sides are equal so that you could show it to your third grade brother and he could say, yes, I can even tell that those two look exactly alike. You don't want to stop with this side saying 1 minus cosine squared and this side saying sine squared. Okay, you want to change that 1 minus cosine squared into a sine squared, and then arrow is showing that the two sides are identical. Okay, that's it. I mean, so it's really nothing new than what we've already been doing. Okay, it's using our identities. The difference is we might work with both sides, right? You might have a problem over here, or the expression over there and the expression over here. You might work with this down for a little while. You might work with this one for a little while, and until they come out to be equal, just depending on the problem, right? Both sides might be kind of weird looking, you know, kind of complex looking, so you work with both. And that's one of the strategies we'll talk about when we come back, is start with the side that's more complex looking, see if you can simplify it down. Okay? All right, so that's called verifying identity. Now, we said that it works for all values of x, or all values of theta. What about pi halves? Pi halves is defined here. You can do the sign of pi halves, but what about here? What's 1 over secant again? Secant is 1 over cosine. What's cosine of pi halves? Cosine of pi halves. No, cosine of pi halves is 90. Cosine's the x value. 0. Pi halves, cosine is 0. So what's secant of pi halves? Undefined. So if we say it's true for all values of x, that it's defined. Pick up that one. All right. I'm sorry. Okay, quickly here. Let's try to get through a few examples so you have a little time to work on some. So what I was saying right there at the end is when we talk about it, this is true for all values of theta, true for all values of x. But that includes, you know, every expression always has a domain, a natural domain. I mean, so if you had an equation that had a 1 over x in it, then you know that x can't be 0, right? I mean, that is not a part of the domain. And so when we have an equation like this where there's a secant in it, think of the secant graph, right, where you have those asymptotes. Or just think of secant as 1 over cosine. So anytime cosine is 0, secant is going to be undefined, right? That's where we drew the asymptotes. If you remember the secant graph, we drew the cosine graph, and every time it crossed the x-axis, we put in an asymptote. So it's it's too good. But you take the cosine graph, and everywhere it crosses the x-axis, you put in the asymptotes, right? Because that's where cosine is 0. That's the x-axis. That's the x-intercept. So 1 over secant, secant is 1 over cosine anytime the bottom is 0, when cosine is 0. So that'd be a pi halves, be a 3 pi halves, and it'd be at multiples of that. So there's a lot of places it's undefined. So just understand that that is something that's going to come in more important when we get into solving some different equations. Because that's what the last two things we have to do, this verifying that something is an identity, that both sides are equal to each other all the time. And then we're going to get into these equations and solving these. We've done some basic ones of this, but now we're going to get into some more complicated ones a little bit starting tomorrow. Okay, so on page 380, so if you look in your book real quick, if you just look in your book on page 380, there's a, and our assignment's in our book today anyway, so go ahead and just leave that out. But there's a box there which says guidelines for verifying trig identities. And so it's got some good suggestions. Work with one side of the equation at a time. It's often better to work with the more complicated side first, so like we did on this last problem. So we worked with the left side, got it to equal the right side. Look for opportunities to factor or to add fractions together like common denominators, to square a binomial, which means FOIL it out, or to create a monomial denominator. What that means, a monomial means one term. So that's when we were putting a denominator together and then maybe be able to flip it or something like that. Okay, so those are things we've been talking about. 3, look for opportunities to use the fundamental identities. Okay, so sine squared plus cosine squared equals 1, right? All those identities we've been practicing. If none of those help, then try converting everything to sines and cosines. Again, stuff we've done. Convert to sines and cosines. Always try something. And this is that part that McKenna, you and I were talking yesterday, and I couldn't find it in the book. That's where I was thinking of. It says always try something. Even paths that lead to dead ends show you something, right? It not only shows you what doesn't work, but it maybe exposes something that, oh yeah, okay, then I could go this way instead of that way. Okay, so always just get started somehow. Do something. Okay, all right, so let's do this one. So go ahead and write this one down. So I just have a couple of them up here I want to try together, just to show you a few of the different things we have. So as we're writing this one down, okay, what would be some, what comes to mind? Which side maybe would you work with, you think? First. What could you do on the left?
Turning cosine.
So this would be 2 over cosine squared. Now that's the Greek letter alpha. If you want to just use thetas or x's when they change those on you, I don't care. And to be honest, once you really get into it, we kind of leave that off anyway, right? We just put secant squared, which is fine for when we're doing these. Okay, that's Greek letter alpha. And then that's about all you could do, right? I mean, there's some stuff you could do. You could write this 1 minus sine squared, which looking at this might be something to do, but maybe I would just wait on that. Okay, so now maybe we go to the other side. Okay, what can you do with this? Common denominator. It's a fraction we're trying to add up, so our common denominator is going to be that, right? So our common denominator is going to be 1 plus sine squared, 1 minus sine squared. Or excuse me, 1 plus sine, 1 minus sine, not squared. Now, you could actually skip ahead a step, because what are you going to do with that problem? You're going to multiply it out, right? Because what's that going to multiply out to? 1 minus sine squared, which is going to be cosine. So we kind of see it coming together already, right? I mean, this bottom is going to be 1 minus sine squared, okay? And we kind of see where we need to go. Now, what's going to happen up here? So to get that common denominator, I need to multiply top and bottom here by 1 plus sine, or it's kind of a bow tie, actually. This is a pretty easy one to bow tie. When you just have ones up here, it's a pretty easy bow tie. So you're just taking that times that. So this is going to have a 1 plus sine up here, and this one's going to have a 1 minus sine. And then the whole goal then is to add those tops together, right? The whole goal is, and again, if you like common denominators, then you can think of it this way, whatever. That's what we did. We took top and bottom times 1, basically. So you're going to have 1 plus sine plus 1 minus sine. Well, what is that? That's just 2, right? Because the signs actually drop out. So you get 2 over, and then this is just going to be 1 minus sine squared, which is just cosine squared, and then you got a match right there. Okay? Now, we could have just left this alone. See, I probably would have thought just start with this side, if Seth hadn't said do this. So I might have got to here. I might have got to 2 cosine squared, 2 over cosine squared. Oh, that's just 2 secant squared. And then I'd have had my maths there and not even worked with the left side at all. It's fine. It doesn't matter. Okay? But once you get to the point where the 2 sides are the same, you're done. Okay? All right. Try that one. You guys try that one. few people done, but let's go ahead and go through it here. Now, I quickly did two different ways. Okay, so somebody tell me what they saw first here. Put that into negative sine squared or cosine squared. Okay, of the two ways I did, I never did that on any. Okay, which is okay. I'm just not going to unveil it yet because I didn't do that. But that'll I'm sure will get you there. Okay, what else? What could somebody else see first?
Tangent squared plus 1 is secant squared.
Okay, so that's what I did. I looked at that one and I saw that tangent squared plus 1 was secant squared. Okay, so one way to do it would be to write that down. Now, from there, what could you do? Do I? Pull a negative out of this, which would turn this into 1 minus cosine squared, which is sine squared. That's what I did in the red. That's what I did in the red there. Okay? Is I took a negative out of that, just kind of did that in my head, and I got 1 minus cosine squared, which would, so that'd be a negative, because you pull out a negative sine squared. So one way to do it is with the red, but then I thought about the blue. I thought, well, you know, if I didn't think of that, I could just distribute this, right? Could do that. Because what's secant squared times cosine squared? That's just 1, right? Because secant squared is 1 over cosine squared times cosine squared. So that's just 1. But if you didn't think of that, what could you do if you had went the red path? What could you do here? Change that into 1 over cosine squared, right? So I kind of got two different tracks going here. So if I stay with the red track, I can make that 1 over cosine squared times negative sine squared, and then just multiply those together. That's negative sine squared over cosine squared, which is negative tangent squared. So there it is. Or if I went kept going with the blue track, secant squared times cosine squared, we said that was 1 minus secant squared. I know I could pull out a negative on that, turn it into secant squared minus 1, which is tangent squared. And that's where that activity yesterday with those identities comes in handy. Knowing all the different versions of tangent squared plus 1 equals secant squared, I know that secant squared minus 1 is tangent squared. And so if I just flip it around, pull out a negative, I get negative tangent squared. And so there it is. So that just shows there's multiple ways. And then if I did what Seth had done, if I would have taken this side, then I could have stopped right here, right? And if I'd have made this negative sine squared over cosine squared, right, then I could have stopped right here. That's a 2, isn't it? Probably 7. All right. I don't know what that is. All right. Let me see. I got a couple. Let's just do one more. Let's do that one. Okay? Try that one. let's just talk about it real quick. There's a lot of different ways you could go with this one, but somebody give me one. First thing to change it. Yeah. And then if you're going to do that, if you're going to change that into cosine squared over sine squared, then you're probably going to do what on the bottom? Probably going to do that, right? I'd be okay with that. Okay. Now what would you do next? Probably have to do something with this, right? And so that means this would be sine over sine. So you get sine plus 1 over sine, and then you're going to, what, flip that? Isn't that's what we've been doing with those, right? So we have this. Now we got sine plus 1 over sine, and we're going to flip it. So up here you're going to get sine over sine plus 1. So what could happen to that? This could cancel one of those sines. So what do we now have? We have a cosine squared over sine times sine plus 1, right? Which I could distribute, but I'm not going to, right? Now what could I do with that? So I'm just continuing to work with this left side. Now what can I do with this? Change the cosine squared into 1 minus sine squared. And then I could do what with that? No. Can't take out a sine from factor, right? 1 minus sine squared would factor into 1 plus sine, 1 minus sine, right? All over sine times sine plus 1. What can I do with that? Cancel the 1 plus sine, and there it is. Now you notice, but I worked it up there, that's not what I did. But it worked fine. A lot, like I said, a lot of different ways. Somebody else have another one. Do what?
Turn cotangent squared into cosecant squared.
See, I like that just because I saw the cosecant down there. And so I saw cosecant down there. I thought, okay, cotangent squared is cosecant squared minus 1. So I went that way. Now ignore this red over here. So I just said, okay, the top is cosecant squared minus 1, which would factor into cosecant plus 1, cosecant minus 1. And that's good because underneath I have a cosecant plus 1. So I can cancel those. Now I got cosecant minus 1. Now I can start getting sines. So now I can take my cosecant, make it 1 over sine minus 1. And then I get my common denominator, so I'd have a sine and a sine here. So I get 1 minus sine all over sine, which is that. So that was a totally, really pretty much different way of doing it. I just waited till the end to get my sines. And that worked pretty good. Now, the other thing I could have done is started with the red and said, you know, I could split this fraction apart. I can make this 1 over sine and sine over sine. We've talked about doing that, splitting a fraction. And 1 over sine is cosecant, sine over sine is 1. So then at that point, I kind of have to stop, right? So then I might come over here and start doing this. So what did I have right here? Right here, when those canceled, I had cosecant minus 1. So I'd have had a match right there. So maybe that's where I stopped. Okay? So, 3 different kind of routes that we could go there. All right. In your book, multiples of 3. So 9, 12, 15, that kind of thing. Okay, 9, 12, 15, 18. So you got some even, some odds. And throw in number 32 because I like that one. Okay, so these are all just like what we just did. Verify the idea. So write it down, give yourself some space, put a T, put that line right in between there just so you're not tempted. It's just a good way to organize your work so you're not tempted to add across the equal sign or something. When we're verifying an identity, we're not solving, so we can't move things from side to side. We're trying to show that the left side is equivalent to the right side.